In the previous discussion, we had seen the position of OH as OH belongs to ring A. This we tried to establish based on the structure called as 3-7 cyclopentano perhydrophenanthrene, which is this particular structure. Here it is 3-7 cyclopentano perhydrophenanthrene. We also said that position number 7 in 3-7 cyclopentano perhydrophenanthrene corresponds to position number 3 in the cholesterol system. So hence 1, 2, 3, this position corresponds to 7th position in 3-7 cyclopentano perhydrophenanthrene, finally establishing that OH is present in ring A. After this discussion about the OH, the next system would be, where is the position of the double bond? Because cholesterol says that there is a presence of one double bond in its constitution. So the next concept that we need to establish is position of double bond. So before doing the position of double bond, we will be doing certain reactions. Cholesterol, upon reaction with hydrogen peroxide in the presence of acetic acid, it gives cholestane triol with the molecular formula C27H48O3 with the Roman numeral 8. This Roman numeral 8, that is cholestane triol, when it reacts with chromium oxide, it is going to give me hydroxycholestane dione with the molecular formula C27H44O3 and Roman numeral 9. Further, the compound hydroxycholestane dione loses a molecule of water and reacts with a system like zinc in the presence of acetic acid. It is going to give me a cholestane dione with the molecular formula C27H44O2 with the Roman numeral 10. Cholestane dione, now this particular compound, which is a dione system, it will react with chromium oxide to give me a tetracarboxylic acid with the molecular formula C27H44O8. Further, the same cholestane dione, that is compound number 10, it will react with hydrazine hydrate to give me a pyridazine derivative. Corresponding to these conversions, now we can observe that certain of the reactions after how they undergo. Now these particular set of the reactions that I have discussed here, now we will be looking for their reactions corresponding to the above conversions. So the compound number 1, that is cholesterol, it is going to react with hydrogen peroxide in the presence of acetic acid to give me cholestane triol. That means the double bond present over here, it is going to get converted to a OH-OH system. Hence, the compound that we are going to get is called as cholestane triol. In this cholestane triol, it is going to react with chromium oxide so that it is going to get converted to hydroxycholestane dione. So what will happen is two OH systems, they will be converted to carbonyl carbon and one OH system will remain intact. Hence, we are going to get hydroxycholestane dione system. When this dione system, it is going to undergo a reaction in the presence of heat, the OH is being lost and then we get a double bond. In turn, we are going to get compound number 10. This compound number 10, it has got a double bond and cholestane dione system. Further, cholestane dione system in the presence of zinc and acetic acid. Now, there is a reduction of this double bond giving me cholestane dione. What will happen is, in the presence of zinc and acetic acid, we will be reducing this double bond and we will be getting a cholestane dione. This cholestane dione, that is complete compound number 10, it will now react with chromium oxide and it is going to give me a tetracarboxylic acid. The system is that there will be a breakage between this particular carbon atoms and 2-3 carbon atoms, and hence we can observe that 1, 2, 3 between 2 and 3 there is a complete breaking down to give me a dicarboxylic acid. Further, if I see 4, 5, 6, there is again a breakage between 6 and 7 where I'll be getting the next dicarboxylic acid. In turn, we will be getting tetracarboxylic acid. Further, the same cholesterol dione, when I observe that cholesterol dione is going to have in the position alpha, beta, gamma system, there is a presence of this gamma system carbonyl carbon. Further, it is going to react in the hydrazine hydrate to give me pyridazine derivative to give me alpha, beta, gamma system in which we are going to observe that there may be a presence of two ketonic system. Hence, with these reactions, there will be certain conclusions that we will be looking for. So the conclusions with respect to these reactions would be the conversion of 1 to 8 represents the hydroxylation of the double bond. Conversion of 1 to 8. Now this shows that double bond is undergoing a hydroxylation reaction. Next, when this cholesterol triol on oxidation with CrO3, cholesterol triol on oxidation with CrO3, it is going to give me hydroxycholesterol. In the previous compound, we saw there is a presence of 3 OH system. But in the final compound, we can observe that only 2 OH compounds are going to give me carbonyl carbon. This tells me that 2 OH systems are secondary in nature and 1 OH is tertiary in nature. That is, this particular OH is tertiary in nature. Hence, it does not undergo any kind of oxidation. Hence, cholesterol triol 8 on oxidation gives a diketone which is 9, that is this compound 9, indicating that in 8, two of the hydroxyl groups are secondary in nature and the third is resistant to oxidation. Next, the oxidation of cholesterol dione. Now this particular cholesterol dione upon oxidation to 10, what is going to happen is first it is going to heat and then there is a loss of water molecule to introduce a double bond. Further, there can be again oxidation with the help of chromium oxide. But before that, what is happening here is after the treatment with heat, loss of the molecule of water and zinc in acetic acid, there is a loss of the double bond, that is double bond gets reduced. Now further, when we get this compound number 10, that is cholesterol dione, the oxidation of this cholesterol dione in the presence of CrO3, it is going to give me a tetracarboxylic acid. Here we can observe that there is no loss of the carbon. Hence, the oxidation of cholesterol dione 10 to a tetracarboxylic acid, which is compound number 11, without loss of any carbon atom. Now, this suggests that both the ketonic groups are present in two different rings respectively. If they were present in one single ring only, if these two ketonic groups would be present in one single ring, then there would be a loss of one carbon atom. But because they are present in two different rings, there is no loss of carbon atoms. In turn, it is going to give me a tetracarboxylic acid. Hence, this tells me that double bond and OH are present in two different rings. With this particular oxidation, we can understand that because there is a formation of a tetracarboxylic acid without a loss of any carbon, we can understand that the OH group and the double bond systems are present in two different rings respectively. Since we have already established that OH is present in ring A at position number 3, now we can easily say that the system of the double bond either can be present in ring B, C or D. Because now we can say that there is a formation of a pyridazine derivative. Now we want to say that ring B is going to have this double bond. We will be establishing that with the help of this pyridazine derivative. Since cholesterol dione system can form a pyridazine derivative with two ketonic groups of compound number 10. Compound number 10 is nothing but cholesterol dione system in the gamma position with respect to each other. Now when I write this system, we can observe that both the ketonic systems are gamma with respect to each other. when I see that this is a carbonyl carbon, alpha, beta, gamma. They are gamma with respect to each other, which is possible only if the double bond is present between C5 and C6. This establishes that now, because the carbonyl carbons are present at the gamma with respect to each other, then we can say that between position number 5 and 6 there is a presence of double bond. When I try to do the same thing, because this gamma position dione system is present, it is going to react with hydrazine hydrate. In turn, it is again going to give me a pyridazine derivative, which is again gamma with respect to each other. Now for example, if I say that this is alpha, beta, gamma, looking at this pyridazine derivative, we can establish that the double bond is present between position number 5 and 6 of ring B. Hence, we can say that at position number 3, OH is present, and between 5 and 6, the double bond is present. But this does not give me the final proof for the presence of this double bond between 5 and 6. Hence, I need to prove it with different type of reactions. Hence, the next concept would be proof for position of double bond. In this particular system, cholesterol, it will react with cuprous oxide at 290 degrees centigrade to give me cholestenone system, that is compound number 12. This upon oxidation with the help of KMnO4, it is going to give me a keto acid, that is compound number 13, with the loss of carbon dioxide. This means that I am going to lose one carbon atom. With respect to these conversions, we will be looking for the reactions. Now looking at the reaction, compound number 1, that is cholesterol, when it reacts with cuprous oxide at 290 degrees, there is this isolation of the double bond from position number 5 and 6 to position number 4 and 5 respectively. This particular compound, which is cholestenone system, that is compound number 12, when it gets oxidized with KMnO4, there is a formation of a keto acid. Now there is a cleavage between position number 3 and 4, and there is a formation of a keto acid. That means a carbonyl carbon and a carboxylic system. That becomes my compound number 13 with the loss of a carbon dioxide. With these particular systems, there are certain conclusions that we can draw. Oxidation of compound number 12 to 13. Now that is the system called as, there is a carbonyl carbon and a double bond in the same ring A. This oxidation from compound number 12 to compound number 13, with the loss of one carbon atom, it indicates that the keto group and the double bond in compound number 12 are in the same ring. We can observe here that the carbonyl carbon and the double bond are present in the same ring. This was also established by the UV spectroscopy, where it said that the double bond and the carbonyl carbon were in conjugation with each other. Hence, lambda max that they observed was 240 nanometer. Now, these results can be explained on the assumption that there is a migration of the double bond. I have already seen that there is a migration of the double bond from 5 and 6 to 4 and 5 of the cholesterol during the formation of cholestenone system. So here in the formation of cholestenone system, that is compound number 12, there is a migration of the double bond between 4 and 5, which is only possible if the double bond is present between position number 5 and 6 respectively. Now this migration from ring number B to ring number A is only possible if the double bond is present between 5 and 6. And hence, from this particular reaction, we can understand that the position of the double bond is 5 and 6 of the cholesterol species. Hence, with this particular reaction, we can establish that from the previous reactions, we established that there is a presence of a double bond. And from the proof for the position of the double bond, through the formation of these keto acids, we could understand that the position of the double bond is between 5 and 6 position respectively. With this discussion, we understood that there is a presence of a double bond and the position of the double bond in the cholesterol species. Thank you.